Okay, so assalamu alaikum and good morning. Today we're going to talk about synchronization in relation to Java. Okay, so we're going to see high-level languages support for synchronization, and our example is the Java language. Okay. We have mentioned before that every object in Java comes with a locking mechanism. All objects in Java. However, the activation of the locking mechanism is done by using the synchronized keyword. Synchronized keyword. So every object has an entry set, as well as it has a wait set, which you're going to see, the time we talk about wait and wait notify. So this object has an active lock because we have called synchronized either on the object itself, okay, or on a code segment, or on a method of that object. Okay. Now, calling synchronized guarantees that there is only one active thread in a synchronized block of this object. So that's the guarantee when you call what? When you use synchronized, okay? It guarantees that there is only one active block, or one active thread in a synchronized block for this object, not more than one, which means mutual exclusion, right? That's what's guaranteed by using synchronized. Other threads who are willing to enter synchronized block for this object are queued in the entry set of the object, and they can. One of them can get hold on the object when the currently active thread who's using synchronized, okay, method or block, is what? Is finished using that method or that block, right? The choice of which one of these waiting on the entry set is done randomly. Now, the way that we use synchronized, you can use it on the whole object. For example, if you have an object X, you can say synchronized X, and then the code in between the curly brackets, okay, that's the critical section of your code in your application that has something to do with accessing X. So in this case, only one thread can access the object X. And the object X, as you know, it might have synchronized method and what? Unsynchronized methods, right? But in this case, I'm saying X as a whole, okay, being locked in this case, right? So X by itself is synchronized, everything in it, which means only one thread can access the object X, regardless of what kind of access is that. We can also use synchronized on a method, only a portion of the object. So you can say a method synchronized, for example, foo is a method that's synchronized, or I can say the body of this method is synchronized, which is equivalent, right? So I can say foo, and the body of the method foo is synchronized by saying synchronize this, and then what? The code of the method inside the curly brackets, as you see in here, which means these two representations are what? Equivalent. They are equivalent. For example, for the producer-consumer problem, if you want to have the insert method synchronized, we can basically say public, where the P here is a small, okay, it's typo. The same thing here, right? Small letter P, okay. So public synchronized void insert, or I can say public void insert and the body of the method being what? Synchronized. So these are equivalent. We usually use this form. Now, properties of synchronized blocks, and the block can be a segment of code within a method, or the whole method, or the whole object, right? The properties is that no other thread can get the lock on X while there is an active thread working with X. That's mutual exclusion. The code within the block that you are synchronizing, whether segment, method, or the whole object, usually is what you refer to as critical section. I think we have discussed this before. And the releasing of the lock is done by leaving the synchronized block. And that can happen for various reasons, including that we have reached the execution of the end of the block, right? So you reach the closing curly bracket, or there was an exit, okay, due to return continue or break, or there was an exception that had been thrown from within the synchronized block. Any one of these will result in releasing the block, which means giving the opportunity for other threads to enter their synchronized block. So when using synchronize, we guarantee what? Mutual exclusion. And when we code, why we use this synchronize, okay, to ensure that our code in the critical section is executed as if it is what? Atomic, okay? As if it is atomic. But that needs an additional code, Synchronize guarantees only mutual exclusion, okay? However, an interrupt, a context switch might happen while we are executing what? Critical section. So that's something that we have to take care of using additional code or additional methods provided by Java. So our code should ensure that the lock is held, okay, within the duration needed to execute what we refer to as atomic code or atomic instructions, set of atomic instructions. And one problem that might arise when doing so is the race condition, okay? So when we use atomic instruction, our aim is to solve the problem of what? Race condition. But in addition to that, we might have additional problems such as a thread blocking other threads from executing, and at the same time, it's blocked from continuing, which means the whole system is what? Blocked. That situation we call it deadlock. Deadlock. And a deadlock can happen for various reasons, okay? System is not progressing, basically. These reasons include, one, threads holding lock may be unable to obtain lock held by other threads. So we might have multiple locks, right? And the thread having some, but willing to have more to continue. However, it can't because it's held by others. These locks are held by other threads. Similarly, the other threads holding these locks, they are also waiting for locks held by the thread who is waiting also for the locks that they have. So everyone like have something, okay, and the other thread want it to proceed, okay? And it might be that a thread is blocked because it's waiting for another thread to finish. However, that thread is blocked. So that also the consequences is that both of them are what? Blocked. The result is that none of them will be executing, which is the situation that we call deadlock. Now we go back to the traditional problem of synchronization, which is in this case producer-consumer problem. Previously we have used synchronized, or we didn't yet, right? Not yet. We used that with the bank account, right? So now if we want to modify the code of the producer-consumer problem, the very first thing is to guarantee mutual exclusion. And to do so, we have actually the insert and the remove methods called by the producer and the consumer, knowing that the producer calling insert and the consumer calls remove. We have seen that these two methods, they share something in common, which is an access to a shared variable, and that is count, right? So what we want to do is to ensure that only one thread can call any of these two methods at a time, okay? That is, in this case, I'm using synchronize for insert and synchronize for remove. So only if a producer is calling insert, then during that time, consumers, they cannot call what? Remove. Because these two methods are what? Synchronized. And a thread already executing any of them means it has hold on the lock of the object. Others cannot have, right? So I ensured mutual exclusion. However, here I have a situation which is something that that's not desired, okay? For example, in the while loop, instead of using a busy wait, okay, we said we want the thread who can't, for example, here a producer who can't insert in the buffer, we want it to be suspended to give chance to other threads to change that situation, which is a full buffer. Okay, so we want the consumer to consume so that the buffer is not full. And here we implemented it using yield. Using what? The method yield. So this thread.yield, okay, suspends the thread who is the producer. So in the code here, if the producer found the buffer full, then the producer is suspended. Okay? Thinking that later on a consumer might call what? Remove. And in remove code, okay, this was full at the beginning for a producer. So when the consumer starts the code here, it will find that it's not empty, right? Because just before now, the producer found it full. And that's why the producer cannot, what? Insert in the buffer. So it will continue here the code, and it try to what? Consume. It will remove an element, right? That's what we are expecting. However, this isn't what's happening. Because the yield method, yes, it suspends the thread. However, okay, it keeps the lock of the object, which means other threads when they run, other consumer threads when they run, they can't get hold to the object. Okay? So what we have in here is very much similar like deadlock situation. Producer suspended itself, but it kept holding the lock. And now consumer cannot consume because the lock is not available. So what we can do is to solve this problem by using other combinations, such as the wait and wait notify methods. The wait, what does it do? Instead of using here yield, a thread who cannot proceed in the work that's supposed to do because of a condition, then it can suspend itself and release the lock as well, right? This is done by wait. So instead of yield, I use what? Wait. As a result of wait, the thread will be placed in the wait set of the object. Wait set of the object. So all of these threads or processes in the wait set of the object, they are what? Blocked. Okay? Blocked. And for them to be unblocked, the method notify or notify all must be called. Must be called. Notify basically picks up a thread from here and place it in the entry set. And by that, giving it an opportunity to execute, to be selected later on and have hold on the object. Notify all, it will remove all blocked threads from the wait set and place them in the entry set, which means giving them opportunity to what? Again, get hold on the object. However, one at a time will be getting hold on the object. So that's how we use wait and wait notify. Wait to block and notify or notify all to unblock. Okay? Now, using this logic, basically, so that's what we shown here, okay? We have wait, at the same time we have what? Notify. Now, whenever you use wait in your application, you must have notify, or at least, or what? Notify all. That's why we say synchronization with the pair, wait, notify, or wait, notify all. Otherwise, you will be, if you use only wait, you're going to have the threads blocked, and that's it. It will stay blocked forever, right? Now, there are some rules with synchronization. These are general rules. The very first rule says that if a thread having hold on the object, which means it has the lock of an object, which means it's executing a synchronized block of the object, right? Then it can it can, within that code, execute other synchronized blocks within the same object. So if you have like two synchronized methods in the object, if the thread is executing the code of synchronized method A, within the code of synchronized method A, the thread can invoke method B, which is synchronized as well, right? You call this situation what? Recursive or reentrant lock. Reentrant lock, right? You don't need to obtain another, you don't need to obtain the lock again. You already have the lock, so it means you granted to access any synchronized method from within synchronized or unsynchronized methods as well. But at the very first bit, you should have the lock, which means you started by having what? Access to synchronized method as a thread. Secondly, a thread accessing a synchronized block within the object means have the lock of that object, might, within the code of that block, might acquire to have the lock of another object, okay? Or more than one object as well. However, we cannot guarantee whether it can get hold on the lock of other objects, right? And that is a situation in which we might have a deadlock. I'm going to show you later how. Thirdly, if a method is not synchronized, then there is no need for a thread to obtain the lock of the object to execute the code of that method, even if there is an already active thread executing synchronized code. Okay? Unsynchronized method, you don't need to obtain the lock. And fourthly, if we call notify or notify all in the logic of our application, while the empty set is, sorry, the wait set is empty, then that will be having no effect, okay? No effect at all on the system. And finally, to use wait, notify, or notify all, okay? You have to be from within. It has to be that kind of usage from within a block that is synchronized. So in unsynchronized method, I can't use wait, right? So make sure if you're going to use these, you're going to use it within a synchronized block, right? As a result of saying so, well, threads in the wait set, right, or in the entry set, or just started, well, as you can guess, we have different, okay, states of a thread, and for the Java, okay, for Java programming language, this is a state diagram that shows you the different states that we have and the transition that causes a thread to move from one state to another. Now let's look at some of the problems in synchronization and see how can we solve these problems, or some of them at least, using wait, notify, or wait, notify, all combination. Okay? We start by the producer-consumer problem. The changes that I have to do on this problem, okay, and actually the main class that we're considering here is what? Is the bounded buffer class, which implements the buffer interface, if you remember. It has two methods, insert and remove. Now the logic of insert, a producer can insert only if the buffer is not full. So that's why we have the condition there. While count equals buffer size, then you can't insert. And in that case, you do what? Wait. Right? Wait. Means block yourself. And I don't know if I mentioned this before, I use while. I said this is a condition, but I use what? While, not if. Can anybody tell me why? Can't I just use if? Right? If I use if, okay, and assume that the buffer is full, then it says if it's full, block yourself, okay, and I'm out already of the loop. So the thread is blocked. The method returns, isn't it? Okay. So while, so that later on when the thread is waking up, right, it will continue in the while loop to recheck the condition. It needs to recheck the condition again, right? If not, then the normal code as you've seen before here. So this is the same code that we have seen before. We have changed yield with wait for the thread to block itself. Now, let's just leave notify here, okay, the discussion of it, and show you the remove, and then we'll get back to notify. Now the remove, again, we did similar thing, okay? If a consumer cannot consume because the buffer is empty, then it blocks itself. But if not, if the buffer is not empty, it will what? Execute the normal code, which is basically getting an item. Now, so here we're saying there are situations in which the producer will block itself and in which the consumer blocks it. So, now whom do you think should awaken the producer who had been blocked? Okay, what is the act, okay, that can awaken a producer who is blocked? A producer was blocked because the buffer was full, right? So the act that can awaken that producer is basically for the buffer to be not full, which means a removal of an item from the buffer, which is a call to the remove method, which is invoked by the consumer. So consumers, they awaken up who? Producers, once they're done, right? So that's why we have the notify here. Okay, if you consumed an item, then check. Okay, notify means check in the wait set. Okay, if there is any producer waiting, wake up one of them. Wake up one of them, notify. And the same thing in here. Okay, a consumer might be blocked because it cannot consume. The buffer is empty. So it will be in the wait set. And the act that will change that, okay, buffer not empty, is the producer producing an item. So after producing an item, okay, then the producer will call notify. And notify will do what? Check. If there was a blocked consumer, then wake up that consumer. Because now we have items in the buffer. So that's how they work together, okay? Wait, notify. Okay, one of the threads will be basically calling notify to wake up what? Threads, either from the same type or sometimes from other types. Clear? Do you have any question about this? So simple modifications to the code. However, it means a lot to us. Now here, wait means release the lock, okay? Change the state of the thread to block, and that will place it in the wait set of the thread, okay? Another problem called the readers writers problem, in which we have a data set, and that data set is accessed by multiple threads, and these threads are of two types. Some of them are readers, others are writers, okay? Now for the data set to be consistent, we want to allow multiple readers to work simultaneously on this data set, because that's won't harm it. They're only reading, right? No problem with them to be active at the same time. However, we only want to allow one writer to be active at a given time without any other writers or any readers. So if you have one writer active, no readers, no writers are active except that writer, okay? But if you have one reader active, then we should not allow writers to be active, but we can allow readers to be active. Readers to be active, okay? We can add one additional thing, which is basically when a writer finished writing to this data set, then the data set should be available for readers and writers, okay? However, when it starts writing, then it should mark this data set as being what? Written, right? So you're going to have a flag for the data set, and that flag will determine whether the data set is written, currently being written, or not. Okay, that's called DB writing. DB writing. Now we can have variations of this problem, in which we favor readers on writers or writers on readers based on the code that we have implement for its solution. An example of this basically is looking files. Now the logic of obtaining the look for readers is different than that for writers. The same thing, the logic of releasing the look for readers is different than that of writers. Just now we discussed the logic of obtaining the look, readers and writers. The writers, the logic is to check whether the DB is written or not. Correct? Because only one writer is allowed. As well as to check some other condition, which is if there is an active writer or no. Right? So two conditions. Two conditions. If any one of them is true, then the writer cannot obtain the look. So it's supposed to wait. Right? If there is an active writer, or if there is an active reader or more, then it should wait. That is the writer. Correct? Yeah. However, for the reader, the logic to obtain the lock is what? Is to check if there is an active writer or not. As long as there isn't an active writer, then readers can what? Can obtain the lock. So two different logic. Two different logic. And the same thing for releasing. Now, releasing of writers, basically the writer, when it finished writing, it will just mark the DB writing flag to be what? Not writing, right? To be false, because the writer is not active anymore. That's the logic of releasing for writers. However, the logic of releasing for readers, if a reader finished reading, then what should it do? Writers we know, right? What about readers? If one reader finished, doesn't mean all readers finished? No. So this act of release is only done by whom? By the last reader. By the last reader. So the logic is different, right? The logic is different, the code is different, and for that we have what? Different blocks for acquiring and releasing readers and writers. Now let's look at the code for these. So basically we have database, this say the data set, okay, and the name of the class is database, and it implements the RW look, which is this interface, right? This interface that provides the mechanism for looking. Now, a class that implements this interface must provide implementation of these four methods. The methods are synchronized, as you noticed. Only one of them can be active at a time, right? Now, what's the code of each one of them? Let's look at the writer first. The writer, the acquirer of the lock, while DB writing, and you see here that DB writing had been initialized to false. It's not been written at the beginning. And I already have readers count, which is an integer that's been initialized to 0. I don't have any active readers. Then the DB writing, okay, this is for the read lock. I said that we will look at the writer first, so let's look at the writer first. The writer says, while reader count is greater than 0, there is at least one active reader, the meaning, or there is an active writer, which means DB writing equals true. If any one of these conditions is true, then the writer will be blocked, who's trying to obtain the lock, right? Otherwise, it will be granted the lock. Otherwise, it will be granted the lock. So if we are here, it means no active writers and no active readers. And in this case, the DB writing becomes what? True. Okay. Now for the releasing, one thing is only done, which is basically DB writing equals false. I've finished writing to the database as a writer. And what else? During the writer writing to the database, there might be other requests from readers and writers, okay? But they'll be blocked because DB writing is false, right? DB writing is true, sorry. DB writing is true. So all of these threads, they will be blocked in the wait set of the object. So now the writer, what does it call? Notify all. If it calls notify, then basically one of the threads who had been blocked, which could be a reader or a writer, will be notified. Correct? And if you assume that a thread is a reader, then only one reader can execute. Right? One reader can execute. The rest of the readers are still blocked. But if I call wait notify, notify all, then all of those who had been blocked will be placed in the entry set of the object. And if the one that had been picked up to execute is a reader, then that will give the opportunity to all readers in the entry set to execute. All of them. Right? Because a reader does not block a reader. So here we are favoring readers on writers. Whoever been waiting, put them in the, place them in the, where? Entry set of the object. Entry set of the object. And if it happened that a reader is chosen from the entry set of the object to execute, that will give the opportunity to all readers in the entry set to finish. Okay? Now what's the code of the reader? Reader lock. The acquire, a reader can only be active if and only if no writer. Okay? Yes? So I have here DB writing equals true means block. The reader is what? Blocked. If not, then the database is not currently being written, and in this case, we can have an active reader. To have an active reader, you're gonna increment the read count, the number of readers, okay? And this code will return means the reader got granted to access the database. Now on releasing, we said only the last reader. So the releasing code, we have list reader. List reader means minus minus reader count. And only the last reader can awaken a thread that had been blocked. A thread that had been blocked. Okay. Now who can tell me which thread can be blocked while a reader is active? Only writers, right? Only writers. So in this case, I have in the wait set home writers only. And why we choose notify? Because anyway, one of them will be active, right? One of them will be active at the time. So we're gonna here notify, pick up randomly one of the waiting threads who are all writers, and place it in the entry set of the object to give it an opportunity to be executed. Okay? So here again, this emphasizes on favoring readers on writers. Readers on writers. If I use here wait notify all, means I'll pick up all the writers and I place them in the entry set. So one will be selected at random to have the look of the object, and then the next time I'm going to select another one, and since they have many writers, so that will increase the opportunity of what? Executing writers. So by that we're favoring writers on readers. So if we exchange notify all in this code and the writers code, then we will do the other type of the problem, favoring readers on writers or writers on readers. Clear? Any question? You grab the concept of wait notify all? That's the most important thing. Of course, we have other problems. For example, this is the dining philosopher problem that we will talk about when we cover semaphores, but I think no harm to introduce it a little bit here. The problem of having like 5 philosophers, okay? Could be any odd number of philosophers. They're sitting around the table, and they're doing, each one of them doing one of 2 things. Philosophers, and they are sitting there. And this is dining table, rounded dining table. There is a rice in the middle, and there are chopsticks placed between these philosophers. So again, Guess I think they are Asians, right? And most likely that rice is Japanese rice. And they're trying to eat it with chopsticks. However, a philosopher to eat rice needs 2 chopsticks, right? 2 chopsticks. Now, if you look at the number of philosophers and the number of chopsticks, equal, right? Now, a philosopher I, if we give them IDs, for example, this philosopher, for it to start eating, it should have access to this and this. Must have hold on 2 chopsticks, the one to the left and the one to the right. So this is the specification of the problem, okay, the problem scenario. And these philosophers, they do one of 2 things again, which is either eating or thinking, right? Eating or thinking. Remember our critical section problem, okay? We have a worker thread doing one of 2 things, either executing critical section or non-critical section. So it's similar, right? Now, what's the critical section? Eating or thinking? Eating, right? Eating. However, thinking is non-critical. Everyone can think, okay, independent of the other. They are not sharing any resources. Eating is critical because they're going to share resources. And if I have this philosopher eating, it means that this and this, the one to the left and the one to the right, they can't eat. Because the chopsticks they need is with this philosopher. At least one of the chopsticks that they need with this philosopher. And having 5 philosophers here, how many philosophers I can have active at the same time eating? 2, in this case, if they are 5, right? So that's a scenario of a dining philosopher problem, which we will show you a solution for using what? Semaphores. Okay, there's no harm of giving you well, an intro to semaphores in 5 minutes. And next class also, I'm gonna repeat that, okay, but maybe in a faster mode so that we can utilize the time. So next is to introduce the concept of a semaphore. Okay, that is a synchronization mechanism, okay, to coordinate access to resources. And if you've seen here that these are resources, these chopsticks are resources, and we have limited number of resources in this system, and these resources are shareable, okay, shareable. So the concept of a semaphore, what is it? In first place, a semaphore is an integer. A semaphore is just an integer with 2 operations. In fact, with 2 atomic operations. Atomic means if the operation started, okay, no interrupt until it's finished. Okay? How is that implemented? You can have your own implementation of a semaphore. Okay, for example, in Java, you can use synchronized wait and notify or wait, notify or, right? Or we can use already built-in implementations of semaphores, okay, provided by a language, okay, high-level language, or by the OS, okay? And you don't have to worry about how these are implemented. However, we're going to show you that there are 2 different implementations of them, and we prefer this on that and so. So, a semaphore is an integer with 2 atomic operations. One operation increases the value of this integer, the other one decreases it. Decrease that value. So it's just an increment or decrement. That's what they do. Okay? But there is something else, because while trying to increase the value, for a condition, we might not be able to increase it. And in that case, there will be blockage. Okay? The calling thread will be blocked. The same thing for decreasing a value. Trying to decrease this value might get blocked as well. Okay? So what do they implement? If I give you an integer value and I say you have these P and V operations where P increments this value and V decrements it, what? Atomically. then can you implement a locking mechanism? A binary lock? A binary lock has two states, right? Locked, unlocked. Locked and unlocked. So if I say that unlocked is 1, unlocked is 1, then I can have a semaphore, initialize it to 1. Okay? Means unlocked. Okay? Now if I call P, what does it do? Decrements. Decrements. Okay? Then if it's 1, it becomes what? 0. It's like obtaining it, obtaining the lock, right? And V does what? Increment. If it's 0, becomes what? 1. So that's the unlock. That is the unlock. But if you notice here, we use differently 1 and 0, 0 and 1, compared to what we used before. Why? Because the general concept of a semaphore is to implement available resources in the system. And these resources, they will be allocated and de-allocated. Allocated and de-allocated, right? So if a system has one resource, which is the lock, then I'll say the value of it is 1. When a thread obtains that lock, then this resource, I don't have any of it. It had been obtained. Then it becomes what? 0. Right? So that's why when you acquire, you decrement, less resources. The system will have less resources. And when the thread who's using the lock finished, then it will release it. Means the system will claim back the resource. So the value will be incremented. Do you understand? Do you understand? Okay. Now, if I have that kind of restriction in my application for the value to be either 0 or 1, only, and knowing that the initialization of this value is 1, then I can say 1 models unlocked, 0 models locked. Right? And who changes unlocked to locked? Who changes 1 to 0? Which method? P. Right? P. Which is acquiring. So P, or acquiring, is the locking, right? And the other way around, who changes the value from 0 to 1? Releases the resource. Is V, which is what? Release, or unlock, right? So that's understanding. If you have it as simple as this, then you fully understand semaphores. With one additional thing, keep in mind that P and V, acquire and release, are atomic. Are what? Atomic. Once they started, they'll be finished, no interruption. No interruption. Got it? Okay, so that's the concept of a semaphore. Now, if I let the value to be more than 1, then I'm implementing what? A resource that has multiple instances. Multiple instances. For example, if I have, in this case, if I have these chopsticks placed in the middle, 5 chopsticks in the middle, they are all the same resource, chopstick, but there are different instances of it. There are 5. There are 5 instances. So I can define a semaphore, okay, and the initial value of this semaphore is what? 5. And then a philosopher to it will acquire, calling P, right? P, to get a resource. And how many times it should acquire? Twice. Call acquire twice. And when a philosopher finish, it will call V, which is release. Twice as well. And that will increment the number of resources because the system is claiming it back. Now, these two concepts, okay, based on how you use the value. If you use it to be 0, 1 only, then you are implementing the concept of a binary semaphore, which is a lock, reentrant lock. However, if you use the value to be more than 1, then you are implementing what is called a counting semaphore to model the number of instances of a given resource. Clear? So that's what we have as an intro to these, okay, semaphores, counting and binary semaphores. The topic is easy, okay? If what I just explained in the last 5 minutes, if you really grab it very well, understood it very well, then everything after that is easy. And this is the most common used synchronization mechanism to solve problems that has to do with coordination of access to shared data. More than that, it has built-in, okay, functions for you to use. So next time, inshallah, we'll talk about them in detail, about semaphores in detail.